All right, let's look at the linked list cycle problem from grind 75. Given a head, the head of a linked list, determine if the linked list has a cycle in it. There's a cycle in a linked list if there is some node in the list that can be reached again by continuously following the next pointer. Internally, POS is used to denote the index of the node that tail's next pointer is connected to. Note that POS is not passed as a parameter. Return true if there is a cycle in the linked list, otherwise return false. So in the example they have, they've got a 3 connected to a 2 to a 0 to a -4, and they're all connected, but the -4 actually goes back to the 2, which means it actually has a cycle. And this example, you've got another example, right? You've got a 1 and a 2, and the 2 goes back to the 1, meaning there's a cycle. And then in this example, because we've only got the one node, there is no cycle. All right, the constraints are such that the number of nodes in the list is in the range of 0 to 10 to the power of 4, some big number, and the value of the nodes is negative a giant number to a giant positive number. POS is -1 or a valid index in the linked list. Follow up, can you solve it in constant memory? All right, so let's take a look at how we can solve this problem. The linked list cycle problem can be famously solved using the tortoise and the hare algorithm, or sometimes called the Floyd cycle finding algorithm. And the way that you typically solve this is with two pointers, which many linked list problems require two pointers. You're going to have a slow pointer and a fast pointer. There are different ways to write the algorithm, but the way I'm going to do it is that the slow pointer is going to point to the first node, and the fast pointer is going to start on the node after the head. And so, for example, if this is the head, and 3 is the head, and so is the slow pointer, and the fast pointer starting on the 2. That's how I'm going to write the code. And eventually what you're going to do is, at every iteration inside of a loop, you're going to move the slow pointer by 1. So eventually this will become the slow pointer, let's say. And the fast pointer will move by 2. And eventually, at some point, if there's no cycle in the list, this fast pointer is going to equal to nil. So if this arrow wasn't here, right, and we tried to advance this fast pointer, it would be equal to nil, meaning there is no cycle. However, because there actually is a cycle, what's going to happen is this fast pointer will eventually catch up to the slow pointer, and then eventually the fast will point to the same thing as the slow pointer. And that's exactly how you solve the linked list cycle problem. In terms of time complexity, right, you're going to have a big O of n time complexity. And as far as space, you're actually not going to need to store additional space, so this can be solved in constant time. It's not a lot of code, so let's just jump right into it. So the way that I'm going to write this algorithm is such that I'm going to handle all the edge cases ahead of time, and that'll lead to a slightly simpler loop. All right, so I'm going to go guard let head, and I'm going to say var slow, which is going to be typed to a list node of optional type, is going to be equal to the head, and the var fast is going to be a list node as well, which is optional, and that's going to be equal to the head.next. Otherwise, return false, meaning we do not have a cycle. And so I'm just going to maybe break these onto different lines to make it a little bit more clear. There you go. It's probably fine, right? And what we're going to do is we're going to say while fast does not equal to nil, go ahead and walk up the slow pointer and walk up the fast pointers until the fast pointer either reaches the slow pointer or it becomes nil, which means there's no cycle. So we're going to say, okay, the slow pointer is going to, at each iteration, equal to the slow pointer dot next, and the fast pointer is going to equal to the fast pointer dot next dot next. And at any point, if slow is equal to fast, we're going to say yes, we've found a cycle. However, the list node they give you isn't equatable, but it is a class. In some of the problems I've noticed on LeetCode, sometimes they'll behind the scenes make something equal to equatable and hashable, and sometimes they won't. In this problem, they didn't, but I'm just going to use the object identity to get around that. So I'm going to say if the slow pointer points to the same thing as the fast pointer, we're going to say yes, we found a cycle. And at the end of this, if fast is ever nil, that means it's reached the end of the list, meaning there's no cycle. We can return false. I'm going to run this code. Looks like a pass. I'm going to submit it. I would expect no problems. And there you go. I hope you've enjoyed this video.